Today we're going to be taking a look at topic 1.8 from APPC or AP Pre-Calculus. This has to deal with rational function inequalities, how the zeros and vertical asymptotes play a role in whether the graph is in positive or negative. We're going to be doing some sign analyses today because we're going to be determining, whether a function is greater than or less than solely based on a sign analysis, not being given a graph. There's no graphs involved, so there's no images. So how can we look and see without actually being able to look and see? So just a reminder that a rational function is a relationship between two polynomials. So there's our rational function is a ratio between two polynomials. You have polynomial number 1, polynomial number 2. Because this is a fraction, the part that creates points of discontinuity are located in the denominator. This value is never allowed to be 0. The reason is you can never divide by 0. So if you had like 5 divided by 0, that would be very not good. However, 0 divided by 5 is 0, so it's doable. So when we say, our denominator is never allowed to equal 0, but our numerator is allowed to equal 0, this is where you find your zeros, also known as x-intercepts. Let's see, there we go. X-intercepts. And in the denominator, because you can't have a 0 there, it creates something known as a vertical asymptote, or an invisible line that your graph approaches but never actually is able to cross. It creates these points of discontinuity. I think is the big concept, just points of discontinuity. So just a reminder, this is exactly what I said up here at the top, is that your numerator, and it's just written in like fancy words, your numerator is allowed to be 0, your denominator is undefined, or it is never allowed to be the value 0, no matter what function is located in that position. So when we're dealing with inequalities, we need to consider all points of discontinuity. Points of discontinuity are zeros, and they are also your undefined values or vertical asymptotes. So there's all of the steps to how to do a sign analysis, and basically what we're checking for is we want to see, is the final product positive or negative? Is it going to be, if this is my graph, is it going to be located in the positive zone, or is it going to be located somewhere in the negative zone? So somewhere down in here, okay? And parts of our graph change. We could have a section that's up here, then it moves down here, then it bounces and stays down here, then it moves back up here, then it finishes down here. So we're using that sign analysis to kind of create a faux x-axis so that we can evaluate what is going on and analyze and interpret that information. So let's start with example 1. The best way to do this is to just jump on in. It is already factored for you. So in the numerator, these values you are allowed to have equal to 0. So I want to kind of look at those first. I am allowed to have x minus 2 equal to 0. If I solve for x is allowed to be 2. This is a good and usable value. So if I'm looking at an x-axis, I have the number 2, and I can use it. Like my graph is physically going to cross at the value 2. My problem, though, is that these values down at the bottom cannot be equal to 0. So I'm going to take each factor and I'm going to say, okay, what values may I never choose from? So if I solve for factor number 1, I know I can never choose the value 6. That is, negative 6. That is not an option because there is a vertical asymptote. I can also never choose the value 3. That is not an option either. There's a vertical asymptote that occurs there. So what I have now on my x-axis is 4 different sections. I have a section located from negative infinity to negative 6, from negative 6 to 2, from 2 to 3, and then from 3 to infinity. And what I want to do is pick values that I can test in a sign analysis that tells me whether or not that particular section is above or below the x-axis. So I need a value less than negative 6. You can choose anything. I'm going to choose negative 10. And I'm going to plug it in to my function. And I want to see what happens. So what I'm going to do is I'm going to take this negative 10, and everywhere I see an x, I'm going to plug it in. And I'm only going to look at the signs. So in the numerator, I'm looking at negative 10 minus 2. That gives me negative 12. So I only care that there's a negative. Negative 10 plus 6 is still negative. And negative 10 minus 3 is still negative. So what I currently have is a negative divided by a positive value, because two negatives will turn into a positive. That entire quotient will end up being negative. So I know that that section, my graph is somewhere down here. I continue through. I need a number between negative 6 and 2. I'm going to choose 0 because it makes math a little easier. So 0 minus 2 is still negative. 0 plus 6 is positive. 0 minus 3 is negative. And I have, in my numerator, I have a value that's negative. In my denominator, that becomes negative. Negative divided by negative is positive. So my graph has crossed over into the positive zone. A number between 2 and 3, I'm going to choose 2.5 because that's limited options here. 2.5 minus 2 is still positive. 2.5 plus 6 is positive. 2.5 minus 3 is negative. So my numerator is positive, my denominator is negative. That whole quotient will be negative. So my graph is under the x-axis. And then something bigger than 3, I'm going to choose 5. Oops. 5 minus 2 is positive. 5 plus 6 is positive. 5 minus 3 is positive. I have a positive value divided by a positive, so this whole section is positive. So what I've done is, even though I cannot see what this function is doing, I do know that it behaves something like there's an asymptote, so it's going to do something like this. Then it's up here, it's going to go through 2, it's going to come down here, and then it's going to behave something like this. Not perfectly, but something like this. So according to my inequality, I am looking for something that is going to be less than or equal to 0. I'm sorry, that says greater than. Lord Jesus. Something greater than or equal to 0. So I am looking for everything that is currently in the green zone. So I go back to my number line and I say, well, this section and this section are both green. That runs from negative 6 all the way up to the number 2. It says equal to, so I can use a bracket. And then it jumps over, picks up at 3, and continues forever. So we're using sign analysis to create like these faux graphs to kind of help us determine which section of our graphs are positive, which sections of our graph are negative. Let's look at example number 2. This one is not factored. So if I look in my numerator, x squared minus 4 can factor into x plus 2 and x minus 2. It's called a difference of two squares, special case. And my denominator, x times x gives me x squared. I am looking for values of 25 that when I multiply them, they make 25, but when I add them up, they make negative 10. So I do know that 5 times 5 is 25, and 5 plus 5 is 10. So negative 5 plus negative 5 must be negative 10. I'm looking for everything below 0. So here's my faux number line, just kind of get an idea of what's going on. My numerator, everything allowed in my numerator can be 0. So I'm looking at x plus 2 is allowed to be 0. X minus 2 is allowed to be 0. Everything in the denominator cannot equal 0. So x minus 5 cannot equal 0. And it is written twice, which means it's going to be a multiplicity of 2. So if I solve for my zeros or my x-intercepts, I know I have an x-intercept at -2, and I have an x-intercept at +2, and I have an asymptote at 5. So over here at 5, there's an asymptote. There's an x-intercept here at 2. And there's an x-intercept over here at -2. So I have, again, 4 different sections of my graph. I have section number 1, section number 2, section number 3, and section number 4. So I want to create testing values that come from each section. So for my first section, I'm going to choose -5, and I am going to replace it or evaluate it into my function. So I'm replacing the x's with -5, and I'm just looking at the sign. Okay. And I want to see what is going on here. Okay. So if I take that -2 and I replace it with my x values in all of my factors, -5 plus 2 is negative. -5 minus 2 is still negative. -5 minus 5 is negative. -5 minus 5 is negative. If I look at that fraction, my numerator converts to a positive, my denominator converts to a positive. I have an overall positive in that first section. So I want a number between -2 and 2. I'm going to choose 0 because, again, it makes math easy. 0 plus 2 is positive. 0 minus 2 is negative. 0 minus 5 is negative, and negative again. So my numerator has a negative value. My denominator has a positive value. So my overall quotient is negative. I need a number between 2 and 5. I'm going to go with 3, and I'm going to plug it in. 3 plus 2 is 5. That's positive. 3 minus 2 is 1. That's positive. 3 minus 5 is negative. Shows up twice. So my numerator has a positive value, my denominator has a positive value, my whole graph has a positive value, and it is moved up. And then the last thing I need to check is something bigger than 5. I'm going to choose 10. So 10 plus 2 is positive, 10 minus 2 is positive, 10 minus 5 is positive, 10 minus 5 again is positive. So I have a positive divided by a positive. My whole graph is positive. So according to my inequality, I am looking for everything that is less than or equal to 0, or sorry, less than, not equal to, which is only this section. So we are going to go from -2 all the way to 2. I'm allowed to choose those values, but my inequality does not want them. It just strictly wants less than. So my interval is -2 to 2. So when we study those, you know, we're looking at what's happening around the x-axis. Whenever we are given an image, I can now ask you anything. So here in example number 7, we have different kinds of asymptotes. We have those vertical asymptotes, and as we can see, they do affect the x-axis. So we can see that those are points of discontinuity. I have a horizontal asymptote. This does not affect my x-axis whatsoever, so I'm not really thinking about it. And then we have a positive section, so that's this, and everything above my x-axis. So all of this is considered positive, and everything below my x-axis is considered negative. So all of this space. So if I look at example A, it is asking where f of x or y is less than or equal to 0. So I'm looking for all the sections that are below the x-axis. So I have a stopping point here and here. So if I look, I actually only have 2 sections, a small little window that is in the red zone. So it runs from -3, it's because it's stuck behind that asymptote, all the way up to the value -1. Then it jumps over, picks back up at 2, and continues down to 3. So it's really just these little sections right here that are living in the red zone. A lot of times students will choose that little middle hump because it's so small, so we want to be really, really careful. Let's see if I can take these off. Okay. Example B is asking for everything strictly greater than 0. So everything in the the green zone. That would be this first section. So that runs from negative infinity all the way up to the asymptote here at -3. So from negative infinity all the way up to -3. Then it jumps over, and this little hump right here is green. That little hump runs from -1 to 2. And then this third section here is in the green zone, and that runs from 3 to infinity. So we could have found those values using a sign analysis if we were given the equation. What would be very difficult is example C. It wants where the y values are greater than or equal to 1. So we have a horizontal asymptote that occurs here at 1. We're looking for the sections of the graph that are strictly above that. So we're looking at, this section here and this section here. So when we have a graph, we can ask you anything above any value. So if we look at that, that runs from negative infinity all the way up to -3, jumps over, picks up at 3, and moves towards infinity. So we use sign analyses to help us determine the behavior along the x-axis, but if I give you the function in graphical representation, then I can ask you for an interval regardless of what the x or y, or regardless of what the y values are. So again, sign analysis tells us what's hanging out, what's happening around my x-axis, and in a graph, you can look at anything that's happening regardless of the situation, because you have the full image. You can see the fullness of the picture.